All right, get ready, because today we're going deep, really deep into GPUs.
Oh, yeah.
Those tiny chips that power, well, practically everything these days, from the latest video games
Right.
to the AI that seems to be taking over the world.
It really is amazing how much we rely on them.
Isn't it? And for this deep dive, we've got a great video that breaks down exactly how a GPU works.
Awesome.
It's not just about what they are, but how they actually do what they do.
Yeah, the engineering behind them is mind-blowing.
Totally.
Yeah.
And get ready to have your mind blown, because we're going to uncover some seriously cool stuff today.
Like what?
Like the insane speeds at which they transfer data. We're talking downloading an entire library's worth of books in the blink of an eye.
Wow.
And hold on tight for this one, because it turns out computers don't just use zeros and ones like we always thought.
Oh, this is a good one.
We'll break it all down, but let's just say things get a lot more complex.
Can't wait.
Oh, and we've also got to talk about embarrassingly parallel tasks.
Embarrassingly parallel.
I know, right? Sounds strange, but it's a real thing, and it's super interesting, I promise.
Okay, you've got my attention.
All right, so let's start with something we can all relate to.
Okay.
You're in the zone, playing your favorite video game.
I love a good video game.
Every character, every object, every little detail you see is a 3D model, right?
Right.
And all those models are stored on your hard drive.
Makes sense.
But when you hit play,
Things get interesting.
your GPU takes over, it grabs those models and renders them in real time, creating that smooth, immersive visual experience that gamers expect.
It's doing a ton of work every second.
A ton.
Yeah.
Because those 3D models contain a massive amount of information. We're talking gigabytes of data.
Gigabytes. Wow.
And all that data has to be transferred from storage to the GPU's memory incredibly fast.
So speed is key.
Absolutely. And that's where the crazy bandwidth of GPU memory comes in. We're talking transfer speeds, reaching a mind-boggling 1.15 terabytes per second.
Hold on. 1.15 terabytes per second.
You heard that right. 1.15 terabytes per second.
That's just, I can't even.
It's hard to wrap your head around, right?
It is. Can you put that into perspective for us?
Okay, imagine downloading the entire Library of Congress.
The whole thing.
The whole thing in a fraction of a second. That's the kind of speed we're talking about.
That's insane.
GPUs are data-hungry beasts.
They need to be to keep up with everything we're asking them to do.
Exactly. So how do they manage to move that much data so quickly? What's their secret?
Well, it all comes down to the bus width, basically how wide the data highway is.
Yeah, okay.
And the really clever encoding schemes used in modern graphics memory like GDDR6X and GDDR7.
Encoding schemes.
You see, we often think of computers working with just zeros and ones.
Yeah, binary, right.
Right, binary is the foundation, but modern memory actually goes way beyond that.
Wait, so it's not just zeros and ones?
Yep. Modern memory uses multiple voltage levels to represent data. It's like squeezing more words into a sentence.
So instead of just on and off, there are more options.
Exactly. More options means they can transmit data more efficiently.
So it's not just about being faster, it's about being smarter.
You got it.
That's really clever.
It is.
So can you give us an example? How does this actually work?
Sure. Take GDDR7, for example. It uses a technique called PAM3, which uses 3 voltage levels instead of just 2.
3.
And that means it can send more bits of information with each signal compared to traditional binary encoding.
So it's like a supercharged signal.
You could say that.
That's fascinating.
And there's another benefit, too.
Oh.
You remember GDDR6X?
Yeah.
It used PAM4, which had 4 voltage levels.
Right.
But by going to PAM3 with GDDR7, they've actually improved things in several ways.
Really?
Yeah, it's simpler, has a better signal-to-noise ratio, and is even more power efficient.
So it's a win-win-win.
Pretty much. Faster, more efficient, and less power hungry.
Amazing. But hold on, we also talked about a different kind of memory earlier. HBM, right? What's the story with that?
HBM, high bandwidth memory, that's a whole different beast.
Okay, how so?
This type of memory is specifically designed for AI chips, and it takes data transfer speeds to a whole new level.
I'm intrigued. How is it different from the GDDR memory we were just talking about?
Well, with GDDR, you have individual memory chips spread out on a circuit board.
Go ahead.
But HBM stacks DRAM chips vertically, connecting them through silicon vias, or TSVs for short.
TSV.
It's like building a skyscraper of memory chips right next door to the AI processor.
So the data has an express elevator to the processing power.
Exactly. No traffic jams.
I love that analogy. So what kind of capacity are we talking about with HBM?
We're talking serious capacity. The newest generation, HBM3E, can pack 24 to 36 gigabytes of memory into a single cube.
A single cube.
And with multiple cubes around an AI chip, you can have a massive 192 gigabytes of ultra-fast memory available.
192 gigabytes. That's insane.
It is, and it goes to show the incredible amount of innovation happening in this field.
It really does. So much engineering just for memory.
Because as our demand for processing power grows, memory technology has to keep pace.
It's like a constant race.
It is.
So we've covered the data and the super fast memory highways, but how do GPUs actually process all of this data?
That's where those embarrassingly parallel problems come in.
You promised this would be interesting.
And it is. It's a surprisingly accurate term for tasks that are easily divided into smaller chunks that can be solved simultaneously.
Okay, but what does that actually mean in practice?
Think of it like having 1,000 chefs all working on different dishes at the same time.
Okay.
Each chef can focus on their own task without waiting for others to finish.
All right, I get the analogy, but how does this relate to GPUs?
Well, GPUs are built for this type of parallel processing. They use a principle called SIMD, which stands for single instruction, multiple data.
Single instruction, multiple data. Okay, break that down for us.
Imagine you have an instruction like adding two numbers together.
Okay.
In SIMD, the GPU takes that single instruction and applies it to multiple sets of data at the same time.
So instead of adding one pair of numbers at a time, it's adding like 1,000 pairs all at once.
Exactly. And it's not just adding. It applies to all sorts of operations, from simple math to the complex calculations needed for graphics rendering or AI algorithms.
So it's doing a ton of work in parallel.
It is, which is a huge advantage when you're dealing with massive amounts of data.
Okay, I see how that would be powerful.
Powerful is an understatement.
But I have a question. If everything is happening in parallel, how does it keep track of all those calculations?
That's where things get really complex. GPUs have a hierarchical structure to manage all these parallel operations.
Okay.
Threads are grouped into warps, warps are grouped into thread blocks, and thread blocks are grouped into grids.
It sounds like a very organized system.
It is. It has to be. There's a sophisticated scheduling system that manages it all.
So each thread is like a tiny worker handling a small piece of the task.
Yes, and the GPU is like a conductor leading a massive orchestra.
It all has to work together in perfect harmony.
Exactly. And remember, each thread has its own data to work on thanks to that massive memory bandwidth we talked about earlier.
It's a beautifully synchronized dance of data and computation.
I like that, a synchronized dance.
This is really amazing stuff. I had no idea how much intricate design and engineering went into making a GPU work.
Most people don't.
But wait, you also mentioned something about SIMD evolving into SIMD.
Oh, yeah, good catch.
What's the difference there?
So with SIMD, all threads in a warp have to execute instructions in lockstep, everyone doing the same thing at the same time.
Okay.
But SIMT, single instruction, multiple threads, allows for more flexibility.
More flexibility, yes.
With SIMT, threads within a warp can progress at their own pace.
So it's like giving each musician in the orchestra a bit of freedom within the overall composition.
That's a great way to put it.
It's amazing how these subtle changes in architecture can have such a big impact on performance.
They really can.
And you know what's really cool? The term warp in GPU architecture actually comes from weaving.
That's right, a little bit of history there.
The jacquard loom from the 1800s used punch cards to select specific threads for weaving patterns. And this concept of warping threads together carried over to how threads are grouped in GPUs.
It's a fun fact.
I love stuff like that. Okay, so we've covered a lot of ground here.
Yeah.
Data transfer speeds, embarrassingly parallel tasks, SIMT. I'm starting to feel like I actually understand how these incredible machines work.
It's a lot to take in.
It is, but it's fascinating.
It is, and we've only just begun.
Oh, there's more.
Oh, yeah. Next, we'll explore the world of Bitcoin mining, tensor cores, and neural networks, areas where GPUs have completely changed the game. What stands out to you so far?
For me, it's definitely the sheer amount of stuff happening at the same time inside a GPU, millions of operations, all perfectly coordinated. It's mind-boggling.
It's an incredible feat of engineering.
It really is.
So ready to dive into Bitcoin mining?
Bring it on.
Yeah.
Speaking of massive computation, let's talk about Bitcoin mining.
Bitcoin mining, yeah.
I remember when GPUs were all the rage for mining Bitcoin, but I never really understood why.
Well, it all comes down to how Bitcoin mining actually works.
Okay.
It's basically a giant guessing game where computers are racing to solve complex mathematical problems.
To mine Bitcoin.
To mine Bitcoin, yeah. They're trying to add new blocks to the blockchain.
Okay, but what does that actually mean? Can you break it down a little further?
Sure. Imagine a lottery.
A lottery.
Where the winning ticket is a random number that meets certain criteria.
Oh.
Miners are constantly generating millions of these lottery tickets every second, hoping to find the winning one.
So it's like searching for a needle in a haystack.
A massive digital haystack.
And the key is to be the fastest.
Speed is everything. The faster you can generate those random numbers, the better your chances of finding the winning ticket.
So that's where GPUs came in, because they could crunch those numbers faster than CPUs.
Exactly. GPUs, with their thousands of cores designed for parallel processing, were ideal for running the SHA-256 hashing algorithm used in Bitcoin mining.
SHA-256.
It's a cryptographic hash function.
Sounds complicated.
It is, but the point is, GPUs could churn through millions of calculations per second, giving miners a significant advantage.
But you mentioned that GPUs aren't really used for Bitcoin mining anymore.
Right. Things changed.
What happened?
ASICs happened. Application-specific integrated circuits. These are chips designed specifically for Bitcoin mining.
So they're purpose-built.
Exactly. And they're far more efficient at performing that SHA-256 hashing algorithm than DPUs.
So it's like comparing a specialized mining drill to a regular shovel.
Perfect analogy.
The ASICs are the right tool for the job.
Exactly. And they've pretty much dominated Bitcoin mining, which has freed up GPUs to focus on other things like graphics rendering, scientific simulations, and of course, AI.
Which brings us to those mysterious tensor cores you mentioned earlier.
Tensor cores.
They sound like something out of a sci-fi movie.
They might sound futuristic, but they're very real, and they're playing a key role in all the advancements we're seeing in AI.
Especially in deep learning and neural networks, right?
Oh, you got.
Okay, I think we need to back up for a second. What exactly are neural networks?
Neural networks are basically a vast network of interconnected nodes.
No nodes.
Think of them as simple mathematical functions.
Okay.
These nodes are organized in layers, and information flows through the network, with each node processing and transforming the data it receives.
So it's like a chain reaction of calculations.
Kind of, yeah. The output of one node becomes the input for the next.
Okay, so what's so special about them?
The magic of neural networks is that they can learn from data.
Learn.
By adjusting the connections between those nodes, they can be trained to recognize patterns, make predictions, and perform complex tasks.
It's like they're learning how to think.
In a way, yeah, it's a simplified model of the human brain.
Fascinating. But I still don't see where tensor cores fit into all of this.
Ah, right. Tensor cores are specialized processing units within the GPU.
Okay.
And they're designed specifically for the kind of math that drives deep learning algorithms.
You mean matrix math?
Exactly, matrix math.
That sounds pretty intense.
It is, but think of matrices as grids of numbers, and tensor cores are really good at performing operations on these matrices, especially multiplication and addition.
Lots of number crunching.
Tons of it. And these operations are carried out in parallel across many elements within the matrices.
So it's like having a whole team of mathematicians working on different parts of a giant equation simultaneously.
You got it. And the speed at which tensor cores can perform these matrix operations is incredible. They can handle trillions of calculations per second.
Trillions.
Trillions, which makes them essential for training and running those large neural networks.
Okay, now I see why GPUs are so sought after for AI.
They're the perfect tool for the job.
It's like they were custom built for the AI revolution.
The parallel processing power of GPUs combined with the specialized abilities of tensor cores has unlocked a wave of innovation in AI.
From image recognition and natural language processing to self-driving cars and drug discovery.
And so much more.
It's amazing to think that these tiny chips are driving such massive advancements.
It is, and it's only going to get more impressive from here.
You also mentioned ray tracing cores earlier. What are those all about?
Ray tracing cores simulate how light behaves in the real world, enabling incredibly realistic lighting and reflections in computer graphics.
So even more realistic video games.
In movies and virtual reality, the possibilities are endless.
Sounds like a topic for another deep dive.
We actually have a whole separate episode dedicated to ray tracing.
Perfect, I'll have to check that out.
You should, it's fascinating stuff.
We've covered so much ground today, from the physical architecture of GPUs to their incredible computational power. I feel like I've gained a whole new level of understanding of these fascinating machines.
Me too. It's been a journey.
It really has, and it's not over yet.
We've still got more to explore.
Well, before we dive into the next topic, I want to leave our listeners with a thought-provoking question.
Okay, I like where this is going.
Considering the rapid pace of innovation in GPU technology, what future applications can you envision for these powerful processors?
Ooh, that's a good one. The possibilities are truly limitless.
It's really amazing to think about how much these tiny chips have shaped our world.
And the most exciting part is we're only scratching the surface of what they can do.
Exactly. So before we wrap up this deep dive into the world of GPUs, I have one last question for you.
Okay, shoot.
We've talked about all the incredible technical aspects of GPUs, the memory, the parallel processing, the specialized cores, but what does all this really mean for the average person? How is this technology actually impacting their lives?
That's a great question. It's important to remember that GPUs aren't just some abstract concept.
Right.
They're at the heart of so many things we interact with every day.
Like what? Give us some examples.
Well, for starters, think about the stunning visuals in video games and movies.
Oh, yeah.
Those are made possible by GPUs crunching through massive amounts of data to render those incredibly detailed and lifelike graphics.
It's true. I never really thought about it that way.
It's easy to take it for granted.
It is, but it makes sense.
And it goes beyond entertainment. GPUs are also powering advancements in healthcare, finance, transportation, countless other fields.
Can you give us some specific examples?
Absolutely. In healthcare, GPUs are being used to accelerate drug discovery, analyze medical images, even assist with complex surgeries.
Wow, so GPUs are literally helping to save lives.
They are. In finance, GPUs are being used to detect fraud, analyze market trends, make lightning-fast trading decisions.
And what about transportation? I know there's a lot of talk about self-driving cars these days.
You're right. Self-driving cars rely heavily on GPUs to process data from sensors, cameras, radar systems, all in real time, allowing them to navigate complex environments.
It's incredible to think how much we rely on this technology without even realizing it.
It really is. It's a testament to the power and versatility of GPUs.
They're not just for gamers anymore.
Not even close. They're essential tools for scientists, researchers, engineers, countless other professionals.
So the next time we're watching a movie, playing a video game, or even just using our smartphones, we can appreciate the role that GPUs are playing behind the scenes.
Exactly. It's all thanks to these tiny but mighty chips that are constantly pushing the boundaries of what's possible.
Well, I think it's safe to say we've all learned a lot about GPUs today.
It's been a fascinating journey.
It really has. And as you mentioned earlier, this is just the beginning.
GPU technology is constantly evolving, so there are sure to be even more amazing advancements on the horizon.
I'm excited to see what the future holds for GPUs and how they'll continue to shape our world.
Me too, and hopefully this deep dive has inspired you to learn even more about this incredible technology and the possibilities it holds.
To our listeners out there, we encourage you to keep exploring, stay curious, and never stop learning.
That's what it's all about.
That's it for this deep dive into the world of GPUs.
Until next time.
Happy computing, everyone.